I'm going to get rid of this triangle. You don't really need that. You don't actually have to break this into components manually in this class. But the point is, we know that this does have a component that is parallel to the polarizer. That's the component that it gets through, but that component is less than the overall vector. So these oscillations should be smaller in amplitude. How would you psychologically register that? How does a person psychologically register?
It's less bright.
Yeah, it's dimmer. That's right. It gets dimmer. So you would see dimmer light after it goes through the polarizer. Okay. So that would give us this after picture over here. There was something I wanted to say, now it's slipping my mind. Let's see. Oh, so going back to our examples again, now we can summarize. The polarizer lets through only the component of the original light that is parallel to the polarizer. The polarizer lets through only the component of the original oscillations that's in the direction of the polarizer. I guess this would work with the fence example too. If I was shaking my rope diagonally, you actually would see some up and down vibrations on the other side of the rope, but they would be milder than the vibrations on my side. So it would work in that case as well. The only case, so the polarizer lets through the component of the oscillations that's in the same direction as the polarizer. So in this case, the entire vector was in the direction of the polarizer. So this intensity would be the same as this intensity. On the other hand, here, in this case, there is no component of the original light that's parallel to the polarizer. Here, the original light is perpendicular to the polarizer. There's no component that's parallel. So this is the only case when the polarizer lets through no light. That's like if I'm shaking my hand left and right, and the fence slats are up and down. Here, there's one component that's parallel to the polarizer and one component that isn't. So you get one component that gets let through. Okay, so these are all the different possible cases that you could see. So we can do a couple examples here. So let's say, before we get quantitative, so let's say you start with light that's unpolarized. We start with unpolarized light, and then we pass it through two polarizers. First we pass it through this polarizer, then we pass it through this polarizer. What will it look like after it finally emerges?
Nothing.
Yeah, it'll be nothing, because what will the light look like at this point?
Like that.
It'll be just left-right. But this doesn't have a component that's parallel to this polarizer, so now it'll be reduced to 0. On the other hand, now let's take this polarizer and turn it like this. Now let's draw what the final light will look like. So here's the first polarizer, here's the second polarizer. Let's draw the final light. Good. So when the light originally gets through the first polarizer, the light is oscillating. I'm just running out of space, so I'm drawing it small, but the light is oscillating like this, left and right. And now this does have a component that is parallel to this new polarizer. There is a component that's parallel to the new polarizer. So there will still be some light, finally. So the interesting thing that you can do in the lab is you can have two polarizers and you can slowly rotate one of them. And you can see that as you rotate one of them, this goes from bright to dark, to bright to dark. Because when these two polarizers are parallel, this polarizer doesn't cancel out any of the light. And when these two polarizers are perpendicular, the second polarizer cancels out all of the light. And there's a bunch of intermediate cases where it just cancels a component of the light. So you have an oscillation from bright to dark. Okay. Again, the naive person would think that these two polarizers would cancel all the light because this is not in the same direction. But now we know to think in terms of components. Okay, so that's the effect of having more than one polarizer. And I guess the last thing to do now is to be quantitative and to figure out exactly what intensity of light gets through. So there's an equation for that that we have to look at. Okay. First of all, let's just draw what the light will look like. Just draw what direction it will be oscillating in afterwards.
The same direction as polarizer.
Yeah, same direction as, yeah. And is it going to have greater or smaller amplitude than in this picture? So I'm trying to draw this. By the way, as a reminder, again, we're following the convention of only focusing on what's happening to the electric field. The magnetic field is always just getting polarized in the same way, but perpendicularly. But we just have to focus on the electric field. That's good enough. So it's going to look like this. I've also drawn these arrows shorter than these arrows, because only a component is going to get let through. So this light will be less intense. And this equation here just tells you how much less intense it's going to be. So this is the new light. This is the old light over here, and theta is the angle between who and who.
Polarizer and original light?
Yeah, so if I hold the polarizer over here, maybe I'll draw the polarizer as a dashed line. Theta is the angle between the polarizer direction and the original direction of oscillation. Theta is the angle between the direction of oscillation of the electric field and the preferred polarizer direction over here. And that's simply what you would plug in to theta in this case. It's not too hard to, this should be a cosine. It's not too hard to prove this, but it's probably not a use to our time, so we won't prove this, but it's pretty straightforward. We shouldn't be surprised that it depends on trig, because basically we're just breaking this into components over here. It would be very easy to figure out the component. In fact, you can really almost just do it. You can see it's the cosine that gives you the component that's parallel, right? So why do we have a squaring here? Well, the key thing is that the amplitude here, you would expect, would just depend on the cosine. However, intensity is proportional to the square of the amplitude. That's actually worth knowing. Both the intensity and the amplitude kind of measure how bright the light is. Both the intensity and the amplitude measure how bright it is. But the intensity is proportional to the square of the amplitude. So you would expect that the amplitude here would be getting multiplied by the cosine of theta, but the intensity is what we really care about, and the intensity then is going to be proportional to the square of the cosine. I'm sorry, you were saying?
This is the square of the amplitude, is the intensity?
Yeah, the intensity is proportional to the square of the amplitude. That actually is a fact that you might need on the test. So intensity and amplitude measure the same thing. They both measure how bright the light is. But the intensity, you can see obviously if the amplitude increases, the intensity would increase because one's proportional to the other squared. But yeah, so they're not, the intensity is proportional to the amplitude squared. Okay, remember what is the amplitude? The amplitude is the maximum displacement of the oscillations. So the amplitude is this distance. It's how far the crest gets from equilibrium, or how far the trough gets from equilibrium. So in our little drawings on the board, the amplitude is kind of how long these little arrows are.
So when I find S, there's some equation, like in one of the flowcharts, there's some equation. Like, I don't use it's like something divided by C or something like that.
Yeah, so this is the same S that we put into our flowcharts. So you could add this to your flowcharts. We didn't go through this in the flowcharts, but then you could use this S to figure out other things. For example, we could figure out the radiation pressure from, this would be a good exam question, we could figure out the radiation pressure from this new light after it goes through the polarizer. Because this is one of the equations that you have in your flowcharts that we talked about previously.
Yeah, from the spaceship that gets pushed.
Yeah. So if something is absorbing radiation, we saw that its radiation pressure is the intensity over C.